Hello, I hope you had a good weekend. I've started looking over your research papers and I'm really enjoying them so far. I do want to ask though, there were a couple people that submitted it under the assignment April 22nd mini research project, and that's partially my fault. I should have been a little bit more clear, so I apologize if I confused you. I only meant that assignment to for you to be able to submit the topic that you wanted to talk about. That way, for especially for people who chose to talk about something that wasn't listed, that I just have an idea of what everyone was planning to research. So that was not where I actually wanted you to submit the paper. That was a separate assignment called mini research paper, and so it makes it a lot easier for me to be able to grade and give feedback when you submit it as a Word document or PDF instead of just typing it into the text in the April 22nd assignment. So for those of you that accidentally submitted it there, would you please do me a favor and just copy what you had, put it in a Word document or PDF, and resubmit it. I won't take off any points because that was partially my fault for not explaining it better. So it's not like you lose points for being late, but it would make grading a lot easier for me. So yeah, if you could do that, I'll try to get those back to you as soon as possible. So make sure anyone who put it in the wrong place or even just hasn't had the chance to get it done, get those in and I will get them back to you. So that would be great. For this week, I wanted to take today to just go over a little bit more with frequency and some of the things we talked about last week, especially for those of you that don't participate in music. A lot of what we've talked about has been very technical, and I want to make sure that everyone's understanding these concepts. Go a little more into depth with changing frequency for each note, how you can calculate that. So I'm going to jump into the PowerPoint slides so that you have some visual to go along with what I'm talking about. But someone asked about how the frequency is changed for each note on a scale. And when Mr. Bray did his video about harmonics and overtones, so the main point with that was that when you have a standing wave, we hear the fundamental wave. So there's a main sound that you hear, especially when you don't have as a pure sound. So if you play a frequency generator online, you're going to have just that frequency, that note, and nothing else. But when you play a guitar string or you blow into a tube, you're going to actually have multiple frequencies going on at the same time. And all of those overlapping frequencies that are there, those extra ones that are above the fundamental, those are the overtones. And Mr. Bray demonstrated how you can change the note that you have by changing the length of the string. So you can go from one note to an octave up by doubling the frequency. And he also talked a little bit about the fifth. So there are 8 notes in a scale. The one here starts with A and goes up to A, I think mostly because it's 440 is a much more round number than C, which is 523. C is oftentimes the note that would be the basis of the scale because of a piano, but it doesn't really matter. It's more of the idea that there are, like, so if you go A, B, C, D, E, F, G, A, that's 8 different notes. So if you go from the low A to the high A, an octave above it, you double the frequency. And I was asked about the change in frequency between each step or half step. And so I have this little chart here to try and show that there isn't an exact way that you have from, so like from A to A sharp, it's 440 to 466, so that goes up 26. But then from the A sharp to B, that 466 to 493, that is, I believe, a change of 27. So yes, so from 26 to 27, and then from B to C, it ends up going up 30. So you can see that each step is going to get incrementally bigger. So that's why we only really focused on the change between octaves as being double, because there isn't a nice, easy way or formula of knowing that. And that kind of makes sense that it wouldn't be the same, because if you think So from this A to this A, if you double it, you're going to have a change of 440 hertz. But if we want to go from this A to an octave above that, you're going to double 880. So a difference of 880 hertz. So the higher on a scale that you get, the higher notes, the bigger difference in frequency between them there's going to be. So there's a lot less difference between two very low notes as there is between two very high notes, even if they're only one step apart on a scale. So hopefully that covers frequency and like the change between them. So even though it's not very easy to know exactly how much the frequency is going to go up between each note, there is a nice equation for calculating the length of a pipe based on the note that you're going to hear when you play it. So I'm going to go into that and use my little plastic straw here that I found as an example. So we know from before that velocity is equal to the frequency times the wavelength. And but if we want to find the length of a straw needed to produce a certain pitch, we're going to use the equation L for length is equal to C, which is what we call the speed of sound. So instead of using V, we'll use C because it's specific to the speed of sound in air. Divide that by the frequency and then divide all that by 2. So I'll go back a little bit more. So the reason that we do C divided by F is we want to solve for the length of the straw with relation to the wavelength itself. So to solve for wavelength, we are going to use this equation V equals F lambda and solve for lambda. So that will be V divided by F, or in this case, C divided by F, because we're talking about the speed of sound. And then to go from wavelength to the total length, if you remember on a tube that has open on both ends, the fundamental is going to be a single antinode. So the wavelength will be double the actual length of the straw. So for that reason, we end up dividing by 2 when we have the wavelength. So because there will be 2 times what you have of this length is going to be the actual wavelength, we divide by 2. If we were using a straw that was closed on one end, we would divide by 4 instead. So then we can find the wavelength by using V equals F lambda. We can find length by plugging in that lambda and dividing by 2. So to use an example, I thought I'd take the nice even number, the 880, which was the A on the last slide, and see what length of straw we need to play that actual note. So we're taking that the speed of sound in a room temperature is 343 meters per second. I don't actually know the temperature in this room, so it's possible that it's slightly off, but we're just going to use that. So 343, divide that by the frequency that we want, that 880 hertz, and then we divide all that by 2. And I went ahead and plugged it in, and we should end up getting a length that is 0.195 meters or 19.5 centimeters. So if I go ahead and I cut this straw, oh, there we go. Here's the side in centimeters. So 19.5 here. Okay, so now I have a shorter straw. Let's really hope this works. But the note that I get is hopefully going to be an A. So I have here a frequency generator or tone generator, and I put in 880 hertz, which should match what we calculated for this straw. So let's play this. So, okay, that didn't work perfectly. This straw, might be kind of hard to hear. I don't know how loud this is, but is a little bit higher than the tone generator. And there are 2 possible explanations for that. One, the temperature here is significantly different from room temperature, and that's messing up our calculations. 2, When I threw the ruler on the ground, I moved my finger and didn't cut it at the right length. And I would be willing to guess that that would be the right explanation. So if I play, it sounds like I was off by about 34 hertz. So about, if we go back to our chart, 34, 30 tended to be about half of a note away. For if you recognize that on a scale, that would be about that difference. So it is kind of important to cut at the right length. I unfortunately did not do a very good job of that. But that would be how you calculate the length that a tube should be in order to find a certain frequency. And using that chart, um, you could figure out the exact change that you'd want for each note. There are formulas that you could use to calculate the exact change in frequency by changing the density of something. So, like with the glasses, when you add water, that's making it more dense. There are like formulas for that as well, or for the difference in tension of a string. Those are a lot more complicated, so I'm not going to go through them. But I do think it's still a valuable thing to be able to test. Okay, how much water does it seem like I need to try and get different notes, and play around with being able to kind of make your own instrument. Were we still in class, what I would have had you do was make your own panpipe. So give you a bunch of straws and have you calculate the frequency needed to have maybe 3, 4, 5 different notes. And then as a class, you could have played things, simple songs like Row, Row, Row Your Boat or like Twinkle, Twinkle, Little Star. But that's a pretty simplistic way of having an instrument. Unfortunately, I realize probably not all of you have straws in your house. And if you do, your family may not be thrilled with you just destroying them by cutting them up. But I do want to give you the opportunity to make your own instrument. So the assignment for today is to find something, whether it's straws or cups or um, rubber band to make a guitarish thing or an empty can to make a drum. I'd like you to make something and um, experiment a little bit to figure out how much you need to change to make noticeably different notes. If you really like music and you want to try and get a full scale difference, go for it. If you're understanding how to do the calculations, but maybe like trying to find the exact musical note isn't something you want to do, that's fine, as long as you have a noticeable difference and you understand what you needed to change to make that. So what about the sound wave is different? Is the velocity speeding up or slowing down because of a change in tension or density? Or is it just that the wavelength is changing because there's more room for it to fit here? So that's your assignment. And I would like if you would submit just a really short video. You yourself do not need to be in it, but just showing the instrument that you have, play a note or two or three or whatever you want to do. So that is all. I hope that this is something that's kind of fun, even for those of you that maybe aren't really, really into music, that hopefully this makes a little more sense about like the difference between what we call notes. It all has to do with a certain frequency and why you hear certain sounds, as far going back to the idea of overtones. So as always, reach out, leave a comment, or send me an email if you have questions, and we'll get those papers back to you as soon as possible. And yeah, enjoy this. Have a good day.